model. The model will be given to you. Let's discuss this. Let's analyze each piece. Let me tell you what they mean. This is the accumulated less your value. I'm sorry? This is lowercase n, this is the m, and this is the n, and this is r. I'm going to get to r in a minute, so r. I'm sorry?
It looks like a. Okay, I'm sorry. For our culture.
You use the r you want. You can put an uppercase r if that's what you want.
I always thought that was pi.
This is pi.
It kind of looks the same if you think.
Okay, well, you can stretch it and say that they look the same. That's fine. Okay, this is the principal. Lowercase r is the annual interest rate. Oh. Interest rate. N, lowercase n, number of times the interest is recalculated. We say compounded. Number of times interest is compounded per year. And t, lowercase t, time in years. So let's go back. So if we deposit, we want to have a down payment for our house, let's say 5 years from now. And the amount, accumulated amount, we would like it to be 50,000. So if this is 50,000, how much should I deposit today? And how many years? Whatever number of years I want, 5 years. And the interest would be recalculated or compounded per year with an interest rate of r. Now it also works the other way around. If we want to borrow the principal, how much we will end up paying 5 years from now, because we have to pay it back. If I take $10 from Alex, he will charge me 1% or maybe 2%, and I'll say I can give it back to you in 5 years. But in 5 years, I'll have to pay with interest, and it's going to be way more than $5 or whatever I borrowed, right? So the formula goes either way. We deposit to get the accumulated value later on, or we borrow and then we have to go give back the accumulated value. Okay, so here is a problem. Find the accumulated value of an investment of, I'm going to copy the numbers, and you tell me which one is what in a second. So that's problem 54, sorry. 54 on page 475. Find the accumulated value of an investment of 5,000 for 10 years. I'm not going to write the letters just yet. I'm just going to copy. 6.5 interest. If the money is compounded semi-annually, quarterly, monthly, and continuously. So we have an investment of $5,000. We want to invest it for 10 years. The interest rate is 6.5, and they want us to determine the accumulated value. Knowing that, option 1, they recalculate the interest semi-annually or compound the interest semi-annually, quarterly, monthly, and continuously. I have to identify this information. I have to place it correctly because I have so many letters in there. I have A, I have P, I have R, I have N, I have T. Which one of these 5 is the 5,000? Is it A? The principal. Very good. What about 10 years? What is it? Which letter? Very good. What about 6.5, which, by the way, has to be 0.065? Never is a percent. Very good. It's little case, lowercase r. Perfect. What does semi-annually mean? For what? For which letter? Very good. For N. Great job. Quarterly. Very good. What is it? What is for? Very good. Monthly.
12.
But I cannot just write 12. I have to write n equals 12, correct? And this one, we don't know the formula. Here it is for continuously. There is no n in the continuously. The formula will be given to you. E raised to RT. Of course, P in front. P E raised to RT. And we'll get to that in a minute. So in the graphing calculator, I would like us to do this. Put in all the information we have. So A equals 5,000, in parentheses 1 plus 0.065 divided by x, because x will change from 2 to 4 to 12, raised to its power, it's nt, which is x times 10 years, or 10x. Why did I create this function? It's because I don't want to repeat the same calculation 3 times. I want to put this function in the graphing calculator. Let's do that. So in y equals, let's put in the function. It's 5,000, left parenthesis, 1 plus 0.065 divided by x, close the parenthesis, put the power, and in parentheses, 10x. Because I want to use the table feature, you don't have to do this if you don't want to, with second and table, but I have to go back and adjust because I said this computer has a deep freeze. They cancel everything that I do when I log out. So we want when n equals 2, with n equals 4 quarters, and when x equals 12. So I didn't have to repeat manually the calculations. I created the function. X is the variable. X changes from 2 to 4 to 12. And immediately I got all the results. You have to go over the results because you need the cents. So 9478.19 is the first answer. So A of 2, 9479.19. A of 4 is 9427.79. And the last one for 12 is so A of 12, 9560.92. It's okay if you'd like to repeat the calculations 3 times. So you'll put first 2, and then you'll take the power 20. Then you'll put 4, and you'll take the power 40. Then you'll put 12 and take the power 120. That's fine. I wanted to show you the easy option, or the shortcut, in which you create the function and you just plug it in. Okay, so now the last one, which is the continuous, is 5,000 times e raised to RT, R being 0.065 and 10 being t. Okay, before we do this, I just would like to mention that there are two special exponential functions. One is called common exponential function, and the other one is called natural. And this is the one that is the natural exponential function with base e. Both of them are increasing functions. Both of them have a base greater than 1. So finally, let's determine this, in which there is no need to use the table now. I get out of there with 5,000. And here's where e is. So these two functions are so special that they have their own key. See the 10 to the x? See the e to the x? They're activated with the second key, 10 to the x, and e to the x. So I'm going to use e to the x with second and ln. In parentheses, I will put 0.065 multiplied by 10 years. Close the parenthesis, and now I can press enter. So if the interest happens to be compounded, recalculated, and reinvested every second of the year, then this will be the amount in 10 years. Continuously. So this will be 9577.70. Of course, for 5,000 it may not be such a big difference, but for any other amount, of course, the difference will be much bigger. Yes, please. Yes, yes, yes. The common is base 10 and natural is base e. So far, you graphed two different exponential functions with different bases that we have not done before. You were able to solve a very simple exponential equation. We will look at more sophisticated ones a little bit later in the chapter. And you are able now to look at an exponential function, say it's exponential. You're able to plug in and determine the values of an exponential function so far. And you know that there are two very special, they're so special that they have their own key in the graphing calculator. The common exponential with base 10 and the natural exponential with base e. Okay, our next step is to discuss, I know I have 14 minutes left, so whatever we can do from section 4.2, which deals with the other function, last one, this semester. This is 11. So, of course, 4.2, logarithmic function. I didn't tell you what it was, but we know already a lot about it. What do you think this is?
The inverse of the.
Right, and it's the log function. That's why they're in the same chapter. That's not the only reason. They're in the same chapter because they're inverses of each other. So this will be the log function with the base greater than 1. We don't like it per se. It's a very nice function, however, but we don't like it because the domain is 0 to infinity, yes. It's not a friendly function, what I like to call friendly. Yes, of course, but unless it has transformations and the whole thing changes. Yes, the pure log function, yes. What about the one with a base less than 1? Here it is. If the base is less than 1, this is the log function with base 1/2. I haven't discussed the log function yet. I'm just showing you the graphs. What will be the domain of a log, pure log, not the one with transformations? But what will be the domain of the pure log function? Right. What will be the range of the pure log function? Because it's the inverse of the exponential. Okay. So let's start slowly. So let's go back to our bubbles. Please give me any exponential function you would like to work with. You could say 2 to the the x. So you can say 3 to the x, you can say 4 to the x, or 2.1 to the x if that's what you want. You can say 1/2 to the x, you can say 1/4 to the x, you can say 1/10 to the x. Which one? You want to work with a nice one. Okay, let's work with 3 to the x. Okay. We chose a nice one. When you say 3 to the x, I already pictured the graph in my head, and I see this. The higher the base, the closer to the y-axis. This is 10 to the x, this is 9 to the x, this is 7 to the x, this is e to the x, this is 2 to the x. The higher, the closer, higher the base, the closer to the y-axis. Perfect. Now I would like you to pick 3 numbers. 1 positive, 1 negative, and 0 has to be in among those 3. So give me a positive number, any x you want, because we know the domain is all real numbers. I can plug in anything I want. You said what? Okay, let's do 3 and -2. Alex says, but then why do you ask? I wanted smaller numbers, Alex. I have nothing against 7 and -7. Very good. And now please give me the y value for each. Take a moment and tell me the y value for each. You have to plug it in. You cannot just come up with numbers. It's not going to work, right? So 27, I agree. Perfect. That's why I didn't want to use your 7 and -7. Yes, 1 indeed. Because they were too big, that's all. And?
1/9.
Very good. Do we all agree with 27, 1, and 1/9? Yes? Very good. Perfect. So now I'm going to say this, that the inverse function, f inverse, and here's the notation. The notation is intimidating, but I don't want you to get intimidated. It's just the notation. So log, it stands for log. What do you think the base must be? It has to be the same base. If we are talking about the function having base 3, the inverse function has to have the exact same base, because otherwise it's not going to work. We're not going to get them to be inverses. You understand that if I give you $5 but I take back 10, the addition of 5 and subtraction of 10 cannot be inverses of each other. Is that clear? If I give you 10 and I take 10 away, then no deal. Same thing here. If the original function, the exponential function, has base 3, the inverse function has to have base 3. Is that clear? Okay. So of x. So here's how we read this. Again, it looks intimidating. Please don't get intimidated by it. Log base 3 of x. Log base 3 of x. This is how we read this function. Yes, it's a mouthful, but it's just a function. It's not a big deal. Okay, the next step is that's my opinion, the most important concept in this chapter is here right now. The most important concept. If we understand this concept, very, 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 very important. If we understand this concept, then we're not going to have difficulties when we solve word problems, when we solve exponential and log equations, when we use the change of base formula, etc., etc., etc. Okay? Here it is. First, in plain English, any log equation can be replaced by an exponential equation, comma, and vice versa. Any log equation can be replaced or changed into into a log. Any log can be changed into an exponential. Any exponential can be changed into a log. This is in plain English, but now in mathematical terms, we write this. Log base a of x is a number y, and this part is the log equation. This is what we call the double equivalency symbol. What does this mean? It means that if I start on the right, I get to the left. If I start on the left, I get the right. It goes back and forth. That's all it means. Double equivalency symbol. Double equivalency symbol. So please pay attention for a moment so we understand this and move, remember it for now on. The base raised to y equals x. Counterclockwise, starting with the base. The base raised to y equals x. A raised to y equals x. And this is the exponential equation. So if we start with an exponential, I can get a log. If I start with a log, I can get an exponential. So it goes from left to right and from right to left. And now you can say, this looks wonderful, but where will I use this? Right here, right now. Right here, right now. I want to show you, because I have not convinced you that if we apply log base 3 to 27, we get 3. I have not shown that. That when we apply log base 3 to 1, we get 0. I have not shown that. And when we apply log base 3 to 1 over 9, we get negative 2. I have not shown that. I needed to explain this concept first. So then, log base 3 of 27. I have no idea what this is. But according to the principle of any log can be changed into an exponential, will you give it a shot and tell me how I change this into an exponential? 3 raised to unknown. Excellent. Very good, Alex. Thank you. Raised to unknown equals 27. And now let's determine the unknown. What can the unknown be? No, it has to be one number. Only one number we raise 3 to get 27. No questions asked. Which number will that be? Very good. So that's why when we apply log base 3 to 27, we get 3 back indeed. We continue with log applied to 1. Log base 3 applied to 1. I have no idea what it is, but I know that I can change this intimidating log equation into an exponential one starting with the base. So I start with the base. 3 raised to whatever equals 1. There is only one number that works. So that is 0. So now we are convinced that when we apply log base 3 to 1, we definitely get back 0. Finally, we want to apply log base 3 to 1 over 9, and we have no clue what that is. But we're confident that we can change this into an exponential equation and figure that one out. So what will happen is that 3 raised to something equals 1 over 9. But that something can only be one number. Why do I know that? Because the function is 1 to 1. You can't find 2 different x values that make y blah, blah, blah. So what could that be? Negative 2, that's the only way, right? Because only 3 raised to negative 2 is 1 over 9. So now we are convinced that this is indeed the inverse function. So meaning 3 to the x and log base 3 of x are inverses of each other. Questions? I will stop. I know I have 1 minute left. I just want to write one domain. So 75, and I'll stop after this. We have f of x equals log base 3 of x plus 4. We are only asked to find the domain of this function. Like with the other functions from before, like the square root, we have to write something and solve it. That's something. We need to solve it to find the domain. What do I have to write and solve? Well, I know that this piece must be a positive number. So therefore, x plus 4 must be strictly greater than 4, which means x must be greater than -4, which means the domain must be -4 to infinity.